right, now we're going to discuss force diagrams. Why are you? Oh, I know why. That's my fault. Okay, we're not going to do the bell ringer. We just literally got done talking about these things. Force diagrams. Force diagrams are stupid important to understanding kind of problems in this chapter. Okay, it's the reason why I spend. I mean, no, it's not the only reason. It's one of the reasons why I spend a lot of time in the first two chapters talking a lot about pictures. And the pictures are certainly helpful. Here, they are irreplaceable. I cannot tell you how many times I have talked to a Physics 2 student, and they've gone, I have no idea how to solve the problem. And I go, have you drawn a force diagram? And they go, no. I said, go do it, and then you can ask me questions. And they don't come back. They don't come back because doing the force diagram oftentimes answers the question. So a force diagram is kind of this process where we mechanically try to understand what forces are there using kind of just basic understanding of what we just got done talking about in fundamental forces. Okay? And then you can analyze the situation much better if your force diagrams are done well. So what is a force diagram and how do I do it? Okay. So the first thing you do with a force diagram is you draw a picture of a situation. So what I'd like you to do right now is draw a car. A couple things to do with that car. Number one, especially if you're a good artist, but also if you're a bad artist like me, don't take a lot of time on the picture. Okay? If you want to, that's fine. Number two, because of things that are going to come up later, draw the picture, usually draw the motion going to the right. You don't have to, but it's highly advised that you do draw the picture going to the right. Number three, once again, this is also you don't have to, but I highly suggest, if the object is moving, I would suggest some type of thing in the drawing to show that. So for me, I draw kind of those animated lines behind an object to show you what it's talking about. So here's my picture of a car. Look how pretty it is. Okay, if you don't know how to draw that pretty of a picture of a car, I'll do the basics for you real quick. Okay, okay, so here we go. Let's pull it up. Here you go. So here's how you draw that pretty of a picture of a car. Okay, you start off with the basics, and then you just add detail. That's all it is. It's not that hard. Okay, I don't understand why people it's so hard. It's not that hard. No, you'll notice, by the way, I am breaking the rule I just told you a second ago. That's for a couple of reasons that I'm going to discuss. But what I meant by moving is you could draw animated lines like that. Some people prefer to draw animated lines kind of like this. Okay, that's helpful for different reasons, but something to indicate that it's definitely moving. All right, next. Here we go. So draw a picture of the car. Now you draw all the forces in the form of arrows and label them. Why would we draw a force as an arrow? Yeah, this enters our fourth vector in this. What are our first three that we've discussed previously? Velocity. Correct? Displacement and what? Acceleration, yes. Displacement, velocity, and acceleration are your three so far, and now we've added a fourth in the form of forces. So, how do I figure out what forces go on this thing? Now, you think about our conversation from fundamental forces. Let's start with the easiest. Is this car on a planet? Yes. What force should probably be on it? Gravity. So we draw an arrow from the center of the object, that matters, down, and then we label what that force is. Notice that I'm using the abbreviation. You're welcome to use the abbreviation on these, just F of G. As a matter of fact, some books, we will not in here, but some books will not use F of G, they'll use W. How come? Weight, because force of gravity and weight are literally the exact same thing. Again, in this class, we will use force of gravity. Okay, now everything else, like I said, is electromagnetism. So we don't write F of E everywhere over this thing. We're going to use the common names instead. So what common names of electromagnetism would be on this car? Keep in mind, it doesn't look like this in the picture. The car is in fact moving to the left, which matters here. So that is true. I'm going to wait on that one in just a second. And actually, when it comes to friction, excellent point. We're just going to combine friction and together and just say friction. Okay. we're going to add detail to that certainly later, but for right now, we'll just say friction. And yes, force normal. Which way is force normal got to go? Force normal goes up. The reason I waited on this because that wasn't the next one on the slide.
Force normal usually just the opposite of force gravity?
No. Usually, yes, but that is not a good rule to follow because you're going to find out. For example, let me remind you earlier when I ran into the wall, which way does force normal go? Back that way. If I run into the ceiling, which way does it go? So if I run into the ceiling, it's the exact same direction as force gravity.
So isn't force normal also going, like, pushing against the car that way?
We're going to talk a little bit more about force normal and which way it goes in just a second on a future slide, so I promise that question will be answered. All right, so yeah, we said friction, and then finally, if this was it, the car would not go forward. So what is probably, if you're sitting in a car, what are you doing that's propelling the car forward? Specifically, yes, within that process of driving, what do you, I think you said it over here. Pushing the gas. And pushing the gas makes the engine go, and the engine pushes the car. So similar to what we talked about before, I would use random force. Force of engine on car. Now I had you draw these going to the right. One of the main reasons I had you do that was to indicate this. Depending on how you draw the picture, you can have a different force diagram than me and be completely correct. Okay, so please make sure you always draw that picture. In my case, obviously, force engine on car is going to the left. If you drew it to the right, it should be going to the right, and friction should be flipped in this case as well. Cool beans? All right, let's move on. Next, actually, let's do this real quick. Draw the force diagram of a person just standing there. Go ahead and do that now. Shouldn't take you very long. Draw a rough picture of a person. Shouldn't be long because there's not too many forces acting on the person. What's the easy force acting on the person? Gravity, very good. And what else? Now you'll notice in this case that drawing it on top of the picture, which I actually do suggest to start off with, can be kind of like messy to see where everything's at. So one thing that you could try to do is you still have to draw the picture, but you come over here to the side and draw the forces separately. This is known as so these are force diagrams right here, okay? But if you've been in our engineering class, I think a lot of times they call them free body diagrams. It's literally the same thing, except the second one is free of the body. So you, in this class, you might hear the book or myself use both of them. They're used synonymously. In both cases, you have to draw the picture. The difference is a force diagram, you draw the forces directly on the picture, and in a free body diagram, as it is free of the body, you draw it to the side. I would suggest, I don't require anything here, I would suggest you start with force diagrams until you get very comfortable with what needs to go on them. Drawing them from the center kind of just makes it easier to see what it is that's going on. All right. Few hints on these. Number one, I said this already, but it's very important. I will take off for this. All forces are drawn from the center. I don't want to see like a picture. Let's see here. I don't want to see like a picture of a car here, and then like down here you have a force, and up here you have a force. They're drawn from the center. Number two, I'll answer your question. Forces are vectors and are therefore drawn to size. The size of the arrow matters. We're not going to get out a ruler and draw the exact size, but if they should roughly be the same, I want the arrows to look similar. So definitely don't do this because it's kind of hard to see how long you think that arrow should be. Yes, Aaron Preston.
So if you do the free body diagram, it's just assume that it's from the center of the picture?
It can be helpful. Yes, it's also helpful to draw dots, kind of just to like say this is where I'm drawing from, to represent
like
that
on
center
the picture or on the arrow?
On the before you draw the arrow. So like if I'm drawing a free body diagram, kind of like I did here, over on the side, I'm going to draw a dot before I draw all of my forces. Something like that. Good. Next, number three. You do not need a force in the direction an object is going. I'll give you two examples. Let's say you are an astronaut and you're in space, with Sally, okay? And you throw Sally. While you're in contact with Sally, there would be a force. But the moment you're no longer in contact with her, is there any force of gravity on Sally? No. Are there any electrons or protons pushing on Sally? No. There are no forces on Sally. But what does she do? She keeps going forever. So, do you need a force to be going that way? No. Don't, no pun intended here. No, don't force it, okay? Don't make there be a force there, all right? Or here's another good example. So say you're driving in this car, okay? We said earlier that this force is because you have the foot on the gas. So say you let the foot off the gas. What changes about this picture? That arrow goes away. Are you still going that way? Yeah. Yes, of course you're still going that way. So you do not need an arrow the way that you're going. It does not have to be the case. We'll talk more about that in the future. Finally, number 4 is this. For a force diagram, only ever draw forces on the object, never by the object. This is going to become very poignant when you start to see things crashing into other things. Like if Spainhour ran full speed into that wall over there, okay? Obviously, hopefully obviously, there would be a force normal going back. Yes? But someone could be tempted in this situation to draw force forward because they know there's a force forward. But if there was a force forward, what would that be? What would the force forward be in that case where Spainhour runs into the wall? That would be the force of Spainhour on the wall, right? So would that force go on Spainhour? No, it would go on the wall. In my earlier example where I jokingly, again, hypothetically for anybody on the recording, where Kieser slaps Spainhour in the face, that would be the force of Kieser on Spainhour. Kieser would not get that force, Spainhour would, because it's on him. Does that make sense? So like if I were to punch the wall, you've got to go, oh, there's a force this way. No, there isn't, because that's the force on the wall. We'll practice with this a little bit. All right. Last slide, and then we're going to practice, and then we're going to be done for today. This is basically going over all of the same forces that we did previously, but this is your cheat sheet. If you are struggling with these at all, I want this sitting in front of you, and I literally want you to go one by one and be like, is it there? Yes or no? So, how do I know if it's there, and which way does it go? Force of gravity. Simple. Is it on a large enough mass? And by large enough mass, I'm thinking like, planets, moon, this type of thing would be big enough. And we talked about force gravity going straight down. But let me ask you a quick question. I know you guys are doing notes, and I appreciate that, but stop for just a second and do this for me. I'm going to draw a picture of a ball on a hill. Here's a ball rolling down a hill, and I'm going to give you options on which way gravity should go. Discuss quickly in your group which of these should be gravities, A, B, or C. Discuss quickly. We'll be right back. Hopefully it's quick. Discuss. Which direction should gravity go? Discuss. Discuss. Isaiah. What's up, buddy? Discuss. Oh, we're not talking, so I assume you have the right answer. What's the right answer? Oh, Jaden, what's the right answer?
B.
B. Why?
Because the Earth is like down.
Correct. It's towards the center of the Earth, technically, and the ball doesn't give a crap that it's on the hill. Obviously, it should be down. Very good. Okay. Next. Force normal. Again, we said this earlier, we're going to use force normal when it's on a solid immovable object, and it goes perpendicular to that object. We've already discussed this. The ground would push up, the wall would push back, the ceiling would push down. But let's go back to that hill example real quick. Do it again from the perspective of force normal. So here's the ball again, and I'm going to give you 4 options this time. Which direction should the hill push? A, B, C, or D? Discuss quickly in your group. At least when I do these, guys, if you have no idea, I want you to guess a letter. Look at somebody else in your group and say a letter that you guess it is. Do that in the next 20 seconds, and we'll be right back up over here. What's the answer?
B.
It's B again. And the reason why it's B in this case is because if you zoom in crazy far to these, you're going to see negatives pushing negatives. And what do negatives do to other negatives? They repel. So the correct force diagram on the ball should be force normal is this way, force of gravity is that way. Does that make sense? All right.
Object, not gravity.
What's that now?
It's opposite of the object, not the gravity.
Correct. Force norm, well, not opposite, perpendicular. Like if I have a ceiling that's like at an angle, like this, okay, it doesn't matter which way the ball, like the ball comes into the ceiling from any angle, does not matter. The ball is pushing 90 degrees to the surface, no matter where it's coming from. Next, force friction. It's a lot more complicated than this, but for right now, it's a good place to start to say if it's moving, just go the opposite way. We've already discussed an example where this is wrong, like for the Sally example, floating through space. Remember, I'm combining surface friction and air friction into one for right now. So really, this is it running into air, is it running into a surface? But tension. Tension is there a rope or cable? And if there's a rope or cable, it goes the direction we did this earlier. Which way is the force tension on this mass that's hanging here right now? What's that?
Up.
Straight up. But what if I hang it like this? Which way is tension? Just parallel to the force, in the exact same direction as that particular rope. Now, this is where I say, keep in mind when you do force diagrams, there is no reason why a few of these cannot double up. Gravity's not going to double up because you're more than likely not going to be dealing with multiple planets. But normal could if you got 2 different surfaces, like the dog example. Tension could if you got multiple cables. You can have multiple tensions. Compression, object's pushing out on itself, but over there in parentheses, notice it says, yeah, you're not going to use this one. Spring, it's real simple. Spring, if it's pushing or pulling. And finally, random on there. These notes are already online, so you can copy down this cheat sheet a little bit later so you can get going. Tomorrow we will practice with these. That's pretty much, like, don't need to take a picture. It's already online. Right online. Don't take a picture. Also, I don't want to be in a picture. There's force diagram.